Good evening and welcome to another edition of Nambani Academy. We are currently running a series of videos on chemical equilibrium. We discussed in depth the basic concepts of chemical equilibrium, where we explained now how factors affect equilibrium. We also explained into how can we best apply the Chatelier principle. We went into the steps of applying the Chatelier principle with basic strategy or an analogy that we used in order for us to answer the relevant questions. So this was now for temperature. This was now an explanation in terms of pressure. So we explained now the application of the Chatelier's principle in the best possible way we can. We looked into now especially when working with the factor which is temperature as to how best can one identify whether a reaction is exothermic or endothermic, because for temperature it relies solely on one knowing exactly if the reaction is exothermic or endothermic. So this particular slide was basically just explaining different ways of one identifying if a reaction is exothermic or endothermic. We went into the basic approach of the stoichiometric calculations. Then we said now this stoichiometric calculation is basically the same in most calculations that are involved in chemistry. So what are we going to do in this instance is going to be very easy. We are going to perform calculations trying to follow this now standard approach of calculations in terms of the stoichiometric calculation. Question 5 was given as an example, and we had now question 6 as one of the homeworks that we must do. So I'm quickly just going to run over it, and because the idea of today's session is actually to go into explaining the graphs of chemical equilibrium in conjunction with those of rates versus time. So without wasting any time, let's get straight into it. Carbon dioxide, let me just do this, sorry, accept the people that are joining. So this was now given as an homework activity. So it basically says now carbon dioxide, let me choose the correct pen. Carbon dioxide reacts with carbon in a closed system to produce carbon monoxide according to the following reaction. What does the double arrow indicate in the equation? So at 6.1, we know that now we said if you see double arrow, it basically means now the reaction is a reversible reaction. That is now 1 mark. Very, very, very easy for one to understand. Is the above reaction exothermic or endothermic? The right way of looking into the correct answer is we are given delta H, which is greater than 0. So it basically says at 6.2, the correct answer must be now endothermic. And it says give a reason for your answer is because now delta H is greater than 0. Then it will be 1 for endothermic, 1 for greater than 0, and this will be now your easy 2 marks. Now let's check what the other statement says. It says now initially an unknown amount of carbon dioxide is exposed to hot carbon at 800 degrees Celsius in a 2 decimeter cubed container. the equilibrium constant Kc for the reaction at this temperature is 14, and it is found that 168 grams 168 grams of carbon monoxide is now present. How will the equilibrium concentration of the product compare to that of the reactants? Choose larger than, smaller than, equal to, and give a reason for your answer. Now, let's read this particular question again. How will the products compare to the reactants? So the question basically wants us to know that how will the concentration 6.3, how will the concentration of the reactants be, of the products be compared to that of the reactants? What did we say? We said now we can only look into the Kc value. Let's look at the Kc value. The Kc value is greater than 1. What did we say? I think we wrote it somewhere here to say now if Kc is greater than 1, let me just use a highlighter. If Kc is greater than 1, it means the concentration of the products is greater than that one of the reactants. So we are told that now the Kc is greater than 1 because it's 14, then one can easily with high level of confidence say the correct answer here must be larger than. Why larger than? Because now Kc is greater than 1. So the concentration of the products will be now greater than the concentration of the reactant. That is now what the Kc value actually informs us. If it is greater, it is greater than 1. So that particular calculation was now easy for one to perform or understand, because the question is actually referring to the Kc value. Can we be able to interpret what the Kc value basically says? So the greater the Kc value, the greater the concentration of the products. Now calculate the initial moles. This is now where we are going to perform our stoichiometric calculation. Calculate the number of moles, or the initial amount of, in moles, yes, of carbon dioxide present. So what must we do with this one? It's very easy. We are working with carbon dioxide, carbon solid, carbon monoxide. What does it say? We said now for all our Kc calculations we are not going to work with solids. Then one can easily say at 6.4, very quickly, CO2, and I have now my CO. Then I have my mole ratio, which is 1, 2, and I'm just going to use now the normal ice table, which is now initial, change, and equilibrium. But we said we like our ice now inside the fridge, so that's the reason why the last one will be now concentration. But what is the question here? It says now calculate the initial amount of carbon dioxide. So we're basically looking for that. Initially, do we have a product? No, we do not have a product. Okay, fine. Then what can one say here in terms of ratio? This will be just minus x, small x, minus, okay, plus, because it's increasing, 2x. I will show you how is this going to assist us as we move furthermore, because we are going to use mole ratios. But we are told now that at equilibrium it is found that 168.00 grams of carbon monoxide is present. So what can we do here? We can get the number of moles of carbon monoxide. M is equals to that. So we are told that the mass here is 168, carbon monoxide is 28, then this just gives us now 6 mole. That is now at equilibrium. 6 moles. Six more. This is now the 6 mole. But now let's check what is it that one can do here. It basically says now one can easily say zero plus 2x must be equals to 6, looking at carbon monoxide. Now solving for x, it basically says 2x is equals to 6. This is divided by 2, then x here is equals to 3. So it basically says what, everywhere where I see an x, I am actually going to put a 3. So here it is going to be 6 because it will be 2 multiplied by 3, that is 6. Here it will be just 3. But what do I know at equilibrium? At equilibrium, I'm going to have x minus 3, and I have now the 6. But now what is the formula for concentration? It's C is equals to N over V. So this will be x minus 3 divided by the volume 2 which was given, and this will be just now 3 because it will be 6 divided by 2. So I actually have now my concentrations at equilibrium. What can I do now? I must just write the correct Kc expression, substitute into that Kc expression. Kc is equals to the concentration of CO squared divided now by concentration of CO2. Now you need to ensure that whenever you write your Kc expression, it must be a correct Kc expression, because now there is just 1 mark for the correct Kc expression. We are told also that now the Kc value is 14. Then I'm just going to substitute everything that I have. This will be 3 squared divided now by the concentration of x minus 3 over 2. Then one must do the mathematics, and then when you do the mathematics you find now that x is equals to 4,29 mole. 4,29 mole. So the basic way is there is 1 mark for actually getting this value. There's another 1 mark here for using the ratio that I always emphasize. There's always another mark here for dividing by 2, or the volume thereof, and then there's 1 mark for the use of molar mass and the substitution thereof. So basically it says once you understand, this becomes easy by just following a pattern, because from the pattern itself, obviously what did we do? We calculated the number of moles. Can I quickly just go to this particular slide? Why this slide? Because we are given the mass, we calculated the number of moles. We use the number of moles to get now the change in the number of moles. We used the molar ratio to get the number of moles of the unknown. After getting the number of the moles of the unknown at equilibrium, we calculated that to get the concentration. That is where I am here, the concentration, and from the concentration we used now the Kc value. So basically, this now standard approach of stoichiometric calculation, you must practice it over and over again, but trying to follow each particular step and the sequence thereof, because basically everything that we did here is exactly that. Inputs, Mr. Srami.
No, sir. I'm still following, sir.
Thank you very much, Tapelo.
Okay, sir.
Thank you. Oratile. Oratile. Thank you very much. Then let's look into 651. State how each of the following will affect the yield of CO2. That is now the application, or CO, sorry. That is now the application of the Chatelier's principle. Choose from increase, decrease, or remain the same. 651, more carbon is added at constant temperature. We said now carbon is a solid there. It was given as a solid. Let me just maybe remove it there. It is given as a solid. So we said now only concentration, temperature, and pressure can affect the yield, can shift the equilibrium. So because it is a solid, ladies and gentlemen, it is a solid, then it basically says it will not have any effect. So the correct answer here is it remains the same because it is a solid. We said now only concentration, temperature, and pressure can only affect the chemical equilibrium or the equilibrium shift. The pressure is increased. We only look now into the gases, but now this side I have 1 mole and this side I have 2 moles. So what is the meaning of that? It basically says increase in pressure favors a reaction with now what? Less number of moles. So it basically means the reverse reaction will be favored, and if the reverse reaction is favored, it means now the concentration of CO will definitely now decreases. It's as simple as that. The temperature is increased. The forward reaction is exothermic. Remember we said now this is for the forward reaction, and the reverse obviously will be now exothermic. Now temperature is increased. Okay, so if temperature is increased, it means increase in temperature favors an endothermic reaction. So the endothermic reaction is the forward reaction, so it means more of CO will be formed. That means now the answer there must be increases, and for all this is basically 1 mark each, and the total is 17. So it becomes easy by just following the basic rules or the basic strategies that now we developed in order for us to actually understand and to actually have a way of performing and applying the Chatellier's principle. So this was now the homework activity that was given. So it allows me now to be in a position of saying we did 2 somehow different problems of the application of the Chatellier's principle, calculations, and basically we saw that now whether it is just a standard calculation like the 5.4 we did yesterday, it basically says but the approach is still the same in terms of the stoichiometric calculation. We looked now into question 6 also. We applied the table of the ice table as we call it, but basically the approach is still the same, because now the general rule that we created for stoichiometric calculation, ladies and gentlemen, it becomes now clear, easy and straightforward. So without wasting any time, because I did explain that now today we are going to work with graphs, but we had now to mark this particular homework activity. So without wasting any time, let's go straight into this particular graphs. Graphs are a serious challenge in chemistry, from physical and chemical properties to these ones of chemical equilibrium. But for one to understand these ones, the easier way of doing it is actually by applying the collision theory, number one, when the graph is now for rate of reaction or rate versus time. So for rate versus time, I must say here one is we need now to apply the collision theory. Apply the collision theory. Why the collision theory? Because the collision theory explains now how the rate will be affected by the change now in temperature, by the change now in concentration. So for these graphs, the idea is we are going to look into concentration and we are going to look now into temperature. One will say, I want us now to include pressure, but I don't want to include it under the collision theory. I am going to include it here and say, let's also consider pressure now only by changing the volume. And how are we going to change the volume, ladies and gentlemen? By using C is equals to N over V. It is not part of the collision theory, because collision theory, we did say that we are looking now into what? Into concentration, temperature, catalyst, surface area. No pressure is involved. So I don't want you to get confused and think that now Mr. Nambane is saying pressure is part of now rates of reaction. No, I'm not saying that. I am only saying we are going to include pressure because now we are going to compare chemical equilibrium and the rate of the reaction. So we cannot omit the factor which is pressure as part of what? As part of the factors affecting the equilibrium. So, but how are we going to do that? We are only going to do that by changing the volume, either increasing the volume or decreasing the volume. So automatically that now will feed into our concentration. Then if it fits into concentration, we can be able to apply the collision theory. Number two, we'll need now to apply the Chatelier's principle. The Chatelier's principle. And this now is easy. We apply it now for pressure, apply it for concentration, and then we apply it for temperature. So this will basically explain the changes that we are going to see in all the graphs that we are going to talk about. and there will be few hints as to say what are we looking for. Once we have identified which factor is being assessed, believe you me, everything will become now very easy for one to follow and understand. Now, these graphs that you see here now, they are just basic graphs of explaining before the actual disturbance. The disturbance we said is either increase or decrease. So we can either, for the collision theory, increase the concentration, increase the temperature, but we cannot necessarily increase the pressure. So what are we going to do in order to increase the pressure or decrease the pressure? We are going to change the volume. So we are going to decrease the volume. It basically says we are increasing the concentration. So now that becomes easy. I will further explain when we deal now with a specific factor. Then we need to apply the principle of Le Chatelier also for when we have a problem that is given. But let's first look at this. I'm going to highlight few important things because you have a privilege of getting the e-notes as well. It says now at equilibrium, sorry, it's too thick. At equilibrium, the rates of the forward reaction and the backward reaction are equal. It is true because now we said what? We said now this is a dynamic equilibrium. So the rate of the reverse is actually equals to the rate of the reverse. So here when we have our equilibrium, the rate of the reverse, which is now the solid red line, it's now the same. But what does this basically say to me now? When I look at the two graphs, it basically says I only know that this will be now the forward reaction that will represent the reactants, and now the reverse will start at 0 because now it represents the products thereof. So it basically says if this is the case, we know that initially only reactants are present. That's the reason why we have now the reactants there at the top. Furthermore, the rate of the forward reaction is higher, but with the at the time it becomes now used up, and then we reach the equilibrium. Hence we say now as products are formed, the reverse reaction increases from 0. That is now what we see here, because we are going to say the rate here is somehow between A and B, very steep. Then basically says the rate of the reaction there is faster. So be on the lookout for that. But eventually, once the equilibrium is reached at the equilibrium, that's the reason why we say the rate of the forward reaction equals to the rate of the reverse. That's the reason why, because it is dynamic. It further says now, hence the rates of the graph should indicate that both forward and reverse rates are equal. A typical reaction rate graph when a system reaches an equilibrium is showed now at the right, which is what I explained there. Now for concentration versus time graph is depicted when there is no change in the reactants or products. So I have two here, they basically mean the same thing. Once we see that we have now a constant line here, a constant line here at T1, it basically says now equilibrium has been reached. So this is now before the actual disturbance. We need to understand that. So once the graph starts at 0, just remember it represents the products. Once it starts now at a certain value above 0, it basically means it's the reactants, because I actually know how much of the reactants I do have. So with this being explained, let's move now into factor number 1. And factor number 1 is going to be concentration. This is now going to be factor number 1. Maybe let me write it nicely. This concentration. So this is now factor number 1. But now with factor number 1, what did we say? We said now our reaction is CO gas plus Cl2 gas. Reversible gives us COCl2 gas. So they are all gases. And I am also told that now delta H is negative, so is less than 0. We will use this now for purpose of explanation as we move along. Furthermore, it says now, when we look at this particular graph that is given here, it basically says equilibrium was reached at about 15 seconds. So here we can easily say equilibrium was reached. Now there's going to be a disturbance. What is the disturbance here? Let's identify the disturbance. Disturbance here is increase in concentration of CO. Now let's apply the Chatelier's principle for us to understand. We said bullet number 1 will be disturbance, which is increase in concentration of CO. What will the system do? According to Le Chatelier, the system, it's applying the Le Chatelier. The system will decrease concentration of CO. Bullet number 2, which reaction will be favored? When we increase the reactant, it means we are going to form more of the product. So the only way of decreasing CO is by actually producing more of COCl2. So it means now the forward reaction is favored. If it is favored, what does that mean? It means now more of or concentration of COCl2 increases. Let me not use more for now. Concentration of because we spoke about increase decrease yesterday, so let me just use what we agreed on using. There we go. Then it basically says we understand the application of Le Chatelier's principle. So we are going to take it now into the graph. When we take it into the graph, let me use green as a highlighter. We see there's a huge spike there. Okay, sorry. There is a huge spike here. That spike indicates now a sudden change in concentration, because if you have your volume and you increase the particles, if you have your volume and you basically just now increase the number of particles, this will be now very easy for one to actually notice that there was now an increase in terms of the number of particles. That is what we said also in the rate of reaction. But just to note this for now, to say it will be important for us to note that if we increase the concentration, we will always have that now big spike there. Fine. Immediately after having the spike, we said now the system will try to decrease the concentration of CO. That is the reason why immediately after the spike, the graph must go down, must decrease. The graph must go down, which is now this particular section here, which is now this section of decrease. When one looks into it, the forward reaction is favored. And if the forward reaction is favored, if the forward reaction is favored, it means also Cl2 must now decrease. That is the reason why we also see now a decrease in now Cl2 decreases. Concentration of COCl2 increases. That is the reason why we see now that definitely we have now an increase in the concentration of COCl2. So that is basically applying the Chatelier's principle. Very important. But I'm going to take it now into the rate of reaction as well. Remember, we said we must apply collision theory and also apply the Chatelier's principle. So we have applied the Chatelier's principle. We are very happy with that. Let's apply now the collision theory. What does collision theory say? Collision theory says now, increase in concentration. I'm going to write it down here. Now this is the collision theory. Increase in concentration increases the number of particles per unit volume. And what does that mean? It means now more effective collisions, more effective collisions per unit time, and then faster rate of reaction increases. Rate of reaction increases. Let me write this increases correctly. Increases. Very important. So let's apply this collision theory to the graph of rate. It basically says now, the forward reaction is favored. Yes, we said the system is in a dynamic equilibrium. But the fact that now the forward reaction is favored, it basically means the forward reaction will have a higher rate of reaction. Why? Because now the particles that are being increased by changing or increasing the concentration basically now says what? Increase in concentration increases the number of particles per unit volume. So if we have more particles, more effective collisions per unit time. But now this issue of applying the Chatelier basically explains which reaction, the forward or the reverse, will have now an increase in the rate of reaction. They will all increase because now there is a increase in concentration, but the rate at which the one increases compared to another one, sorry, will definitely be higher. Only because of what? Only because of the reaction that is now being favored. So a reaction that is favored is the one now that basically indicates or shows a greater spike in terms of the rate of reaction. That's the reason why when you see this graph here, it basically says at 20 seconds now, when the equilibrium was reached, or the equilibrium was reached at 15, let me just write 15 here, and then when we had our disturbance here at 20, that is where the disturbance occurred, and then the disturbance also occurred here at 20, disturbance. Then it basically says that's the reason why we see now that the forward reaction actually has a higher rate, but it will eventually decrease such that the equilibrium can now be again at the dynamic equilibrium. So hence we say now the equilibrium here, what is critical is using the Chatelier to actually understand which reaction is being favored. So the fact that one was able to pick it up that actually the forward reaction is the one that is favored, it basically means now when it comes to rate, because of the number of particles, automatically the rate will also increase, but for which reaction? For the forward reaction. Why? Because now applying the Chatelier in link or in connection with the rate or the collision theory, it allows us to actually see and know for sure which reaction is going to have a higher rate. That is very, very important. So the very first one is Le Chatelier, and this is now the application of the collision theory. So the collision theory and Le Chatelier, we are linking the two by so doing. So Le Chatelier tells us now which reaction will be favored, but collision theory tells us now which reaction or how rate of reaction will be affected, increase, decrease, or remain the same. Inputs, Hloni.
No, sir, I'm still okay, sir.
Thank you very much. Oratile. Thank you very much. Tapelo. Thank you very much, because you are going to need now this application of graphs at some certain instance. So that is now factor number one, which is concentration, done and dusted, clear and straightforward. The combination of how will then the rate and the graph of equilibrium be affected. So you can read all this nice English that is written there, but I think the best explanation that one must use is the application of the two. Because even if you read what is on the slide, I think I explained it in a way such now you understand actually why the forward reaction is favored. Because it basically just says here the rate of the graph should not show a sudden spike in the forward reaction. But why? The system moves in a net forward direction, followed by a slow increase in backward direction until both. Exactly, it's what the graph says. But why did now the forward reaction have such a huge spike, not the reverse? Application of the Chatelier together with the collision theory. Then let's move to another factor. We will check which factor is this. This factor is temperature. This factor is temperature. Our reaction is CO plus Cl2. Reversible gives us COCl2. We are told delta H is less than 0. Let me check if I've captured it correctly. Yes, everything is a gas. Everything is a gas. And we are told that it is exothermic. Everything is a gas. Sorry, let me quickly just G and G. Now we need to ask ourselves, what is the disturbance? Very, very important. Very, very, very important. And I'm going to give you now a hint as to say, how can one be able to tell whether it's temperature? We said for concentration, we're going to have this high spikes, sudden big spike indicates concentration. Fine. Now, how can one tell that this is now temperature? Okay, let's have our beaker also and have our Bunsen burner. Let me move it there and put this there. Then maybe I must have a flame and a couple of particles. So when you heat the reaction vessel, it basically says all the particles that are in there are going to be affected, which is true. Let me have a line here to indicate a sudden change in all of the reactants and products we have. Why? Because the change will affect everything that is in there. We are also going to try and apply the Chatellier's principle. So let's check what is happening by just looking at the graph. We agreed that this here must be an exothermic reaction. Exothermic reaction. So what is the disturbance? For me to have an increase in the product, which is now COCl2, we have an increase here. So for me to have an increase, it means I should have favored the forward reaction. So decrease in temperature favors exothermic reaction. So the disturbance is decrease in temperature. That is the disturbance. according to the Chatelier, the system will increase temperature. And we said now the following bullet, we say it as it is according to the factor. Decrease in temp favors exothermic reaction. Ne? And then we further say, okay, fine, which reaction will be favored? Forward reaction will be favored. What will happen to COCl2? Increase according to Le Chatelier's principle. Forward reaction is favored, and then concentration of ClCl2 increases, and the rest obviously decreases. But now it is happening for all of them at the same time. Why? Because they are in one reaction vessel. Remember that. So which reaction is favored? The forward reaction is favored. Very happy. That is what I get from the Le Chatelier. Apply the collision theory. Apply the collision theory. Collision theory. When I apply the collision theory, let me take this, put it here, take that, put it here, and take everything here and put it in back again. But this time I don't need the fire because I decreased most the temperature. So I'm just going to put it out there. What did the collision theory say? The collision theory says now, bullet number 1, decrease in temperature. Decrease in temperature decreases the overall kinetic energy of the particles. Bullet number 2, EA is greater than EK. Kindly write it in full. The activation energy is greater than the kinetic energy. What does this mean? Less effective collisions per unit time. What does it mean in terms of the rate of the reaction? Rate of reaction decreases. And from that, we will be now in a position of saying, if the rate of the reaction decreases, how can we see that in our graph? Very easy. We know the forward reaction is favored, which is the solid line. Sorry, let me use a brighter color. Forward reaction is now the solid line. Forward reaction is favored, but the rate of reaction must decrease. Why? Because there was a decrease now in temperature. That is the reason why you have now this, and both of them will decrease true, but now the forward reaction will decrease more only because of it's a reaction that is being favored. So we are applying the Chatelier together with the collision theory to actually understand how best can one be in a position of ensuring that we understand this particular disturbance of change in temperature, of which in this instance we picked it up, or we identified that the actual change is the decrease in temperature. Inputs, Mr. Sarami.
No, sir. I get the temperature, sir.
Thank you very much. Inputs, Mr. Tapelo, Ezekiel.
I'm still following, sir. No problem.
Very clear, ne?
Okay.
Thank you very much. Now, if temperature is done, it means we are only left now with one factor. What is that one factor? That one factor is pressure. Let's move. It's pressure. Let's move. Let's write the equation down. Change the color. It's CO plus Cl2, reversible COCl2. They are all gases. And then we have 1. And this combined, we have 2. One will say, but in that number, you said when we have concentration, we will see by a big spike. Let me just put this here just to indicate the section of the disturbance. Yes, we are going to have a big spike when it is concentration. But for concentration, we only added 1. In this instance, we increase the concentration of CO, and others only changed later, immediately after doing what? After the system trying to reinstate a new equilibrium. So with pressure, it basically says it affects all the products if the reaction favors the products. It affects all the reactants, provided that now what? The reaction that is favored is the one of the reactants. Now let's see. We have an increase in concentration of CO. This is an increase. We also have an increase here in the concentration of Cl2. So it basically says the reverse reaction is favored. So I'm going now to try and identify the disturbance. So what is the disturbance? Very, very important. For me to favor the disturbance, it means I must actually increase in pressure favors a reaction with less number of moles. So that will not work. So decrease in pressure favors a reaction with a greater number of moles. Those are the basic things that we spoke about in the beginning. So it basically says this is actually a decrease in pressure. And how do we associate it with C and volume? It basically says decrease in pressure basically means increase in volume. Increase in volume. We'll try to explain that for the effect of this particular graph here. Now let's check what will happen here. Because we agreed that, let me go to this point of pressure. Increase in pressure favors a reaction with the smallest number of moles, and then decrease in pressure favors a reaction with the greater number of moles. It is also written there. So in this instance, we have the reactants actually increasing. So it means we need to favor a reaction with a greater number of moles, which is the reverse reaction. So let's look into it quickly. Then let's apply Le Chatelier. According to Le Chatelier, the system will increase pressure, and then what? Reverse reaction. Sorry, we must say now decrease in pressure favors a reaction with greater number of moles. And then here we say the reverse reaction is favored 100%, and then we say more of concentration of CO and concentration of Cl2 increases. It is as simple as that. Increases. Very happy. Reverse reaction. But now let's apply the collision theory. If we apply the collision theory, it will be easy for one to say how does now pressure and concentration relate. Now I am going to say increase in volume basically means decrease in pressure, and obviously decrease in volume means increase in pressure. So for one to explain this, let's have our beaker again. I'm going to have this one here with a greater volume and put particle 1, particle 2, particle 3, particle 4. And then I'm going to have another one with now the same, but now the very same number of particles with a lower volume, which is 1, 2, 3, 4. This is now low volume, and this is now high volume or greater volume. What will this mean in terms of the collision theory and the concentration? It says now the one with low volume here, the one with low volume will have high concentration. The one with high volume will have now low concentration. And this is explained by C is equals to N over V. So if we increase volume, it basically says we are decreasing the pressure. And if we increase the volume, we are going to get low concentration. However, the rate of the reaction for volume decreases should resemble the graph on the right, since a volume decreases, increases the concentrations. Very, very important. So since a volume decreases, increases the concentration. That is what we said. If the volume decreases, the concentration is high. And the products for the forward and backward reaction should also increase. So because it's happening now for all the products or components of the container, so everything there, it's now suddenly increasing. Everything. While even though the reverse reaction is favored, everything in that particular vessel is going to experience the same pressure. So everything increases. Hence you can see there's an increase there. There's also an increase here. So this is basically by this that says we are going to have a high concentration. So high concentration basically means now what? Everything is going to be now favored. But the one that is going to be more favored in this instance is going to be, let me just now confirm, a sudden change in concentration or pressure indicates a volume change. A sharp rise as shown in the diagram indicates a volume decreases. Okay, so I did it now differently. So it basically says the forward reaction will be the one that is now favored. Let me just say here is going to be actually increase in pressure because the volume was decreased. So it's going to be increase in pressure, and let's just correct that. It basically means it's going to be decrease in volume. Yeah, and then basically there it is going to be forward reaction, easy, and then basically it's basically everything that we explained. So the forward reaction will be more favored, but everything will increase because now basically the reverse reaction also be 1 and 2 and the collision theory thereof. So it looks kind of okay, but what is critical is now remember decrease in volume increases the pressure, and then increase in volume decreases the pressure. and by so saying, it says low volume, high concentration. Everything in there is going now to increase because the particles are closer to one another, and if they are now closer to one another, it basically says the particles will collide effectively per unit time, and the rate of the reaction will now increase. That's the reason why we have the graph that we have. Lastly is a catalyst. Remember, no effect on equilibrium shift, only affects the rate of reaction. Then both reactions increases. And that's basically it now with the graphs of chemical equilibria. Inputs, Mr. Tapelo.
I'm fine, sir.
Thank you very much. Mr. Serame.
No, sir, I'm still good, sir.
Thank you very much. Then it basically says I have 2 activities here, which will be homework activities, and that will be discussed when we meet again on Friday. So you will get now immediately the e-notes of this, and I tried to explain the graphs in detail the best possible way I can. If there's a mistake somewhere, kindly follow up with me. I will fix it, but I think this one of pressure, because we did not realize that now there was a decrease in volume, so few things there might also change, but it will be corrected in the near future. That is not a train smash, it's just now applying the Chatelier's principle the right way, and yeah, everything seems to be done the best possible way. For me to you, ladies and gentlemen, thank you very much. It is exactly 1954. So let's basically meet on Friday 6 o'clock for that 1 hour session. That is where we only just mark our activities that were given on Tuesday, so that we ensure that we actually know and what to prepare for. Be on the lookout also for the new schedule to assist you for those that are going to write June examination next week. Be on the lookout for that also. Thank you very much. For me to you, thank you very much, and have a lovely day.